So our last talk is going to be in person, as you can see. The speaker is over here. So prepare your questions, and we can ask double the questions this time. So prepare. So it's a great pleasure to welcome Francesco Tanni. I think not to the first time to the campus. So Francesco is an experimental physicist, and he leads a Max Planck research group at the Institute for the Science of Light in Erlangen. So he's been here before. His master's degree from the University of Rome in 2010. And after completing his studies there, he went to the Erlangen, where he did a master's and a PhD with Philip Russell, working on photonic crystal fibers. In 2016, after 2 years of postdoctoral research in the division, he became the team leader for the ultrafast nonlinear optics group. In 2021, he received an Italian scientific qualification and, with other collaborations, a Pathfinder grant from the European Innovation Council, with which he started a new research group in cryo-optical spectroscopy. The main focus of Francesco's work is ultrafast nonlinear fiber optics. He's investigated a wide range of nonlinear optical dynamics and PCFs, combining fiber optics with high field science, pioneering the study of filamentation-like and long-lived dynamics in fibers. Building on his research, he's developed novel sources of ultrashort light pulses in exotic spectral ranges and worked further on these in collaboration with industrial partners. Today, he's going to talk about extreme nonlinear fiber optics. Francesco. Do you want this?
Thank you very much. It's a very pleasure to be here. I just realized today that it's 10 years since we met the first time in Germany. I'm going to tell you about extreme nonlinear optics in fibers, especially PCF. Here you can see one of these fibers when we put that's in a gas cell filled with gas and then sends into its very short pulses. So maybe for sure, at least for me, we can get very extremely nice pictures. So in our work, we combine nonlinear fiber optics, which thrives on Soliton dynamics, very long interaction lengths, where the dispersion can be controlled and typically deals with low photon energies. And we combine all this with ultrafast science, where very often we deal with much shorter pulses, femtoseconds, attoseconds, intensity above the ionization threshold, very often high order nonlinearities, and often high photon energies. Of course, the two fields have been interacting for a long time. We can think of fiber lasers, or we can think of the collaboration between Ted Dench and Philip Russell. But here, I'm really talking about bringing the two fields together. So essentially, we take ultrafast science and we put it inside a fiber. And then, if we do this, we can open, we can have a wide range of new possibilities of things that we can do. And for example, we can use these fibers, this system for generating ultrashort pulses at high peak power and high repetition rates, or for generating radiation in exotic spectral region with very short duration, for studying photoionization and filamentation-like dynamics in a very well-controlled environments for spectroscopy. And this is a work we can also, which we had recently, which if we just send, we mix particle trapping with ultrafast science, we can actually build micro rockets. So this is actually a very nice work. I really like it, and I encourage you to ask questions if you want, but I'm not going to tell you during this talk. So if you're curious, I'm happy to answer questions. And then similar system, in this system, this is not directly my work, but just to show you how rich and variegated such system would be. It can also be used to change the frequency of single photons. And this has just been recently published by my colleagues, Nicolas Joly and David Nouveau. So I will mostly focus on the first three parts. So how to use such a system to generate very short pulses at high repetition rates and change the frequencies, and also how what we can learn from what the ionization, and we use this to improve our sources. And the idea here is to realize sources of single cycle pulses at tens of megahertz repetition rates in any spectral regions, and which are just turnkey. So why do we need such sources? There are many different applications. I think I don't need to advertise this too much here in Ottawa, but of course for light wave electronics, strong field physics, to generate high harmonics with high brightness, or for time-resolved tunneling scanning microscopy, or even to accelerate electron beams. And for many of these applications, you don't need very high pulse energy, but you do need high repetition rates, because the signature can be quite weak, and high repetition rates helps improving measuring and observing these signatures. Of course, there are many other applications, such like the generation of frequency, and especially dual frequency comps in spectral regions which you cannot access with other methods, especially the UV. There are no dual frequency comp reported yet. Then you can explore novel nonlinear fiber optics dynamics, and you can also use such sources for much more practical applications, such as 3D photon microscopy, cars, semiconductor characterization, and even the development of new photodetectors. So these are the fibers I'm going to tell you about. These are anti-resonance reflection fibers. We can see on the left Kagome fiber. These are SEM pictures. The gray area is glass, the rest is solo. And here it's a single ring or revolver or tubular fiber. Everyone calls this in a different way. The structures are quite different. However, for what we're interested in, these are exactly the same fiber. So there are some differences, but this is not relevant now. And then if we put one of these fibers under the microscope, you can see that you can get very white lights in the core, which means that it has a very broadband guidance. And in fact, these fibers can have transmission windows spanning over hundreds of terahertz, so hundreds of nanometers with very low loss, even below telecom fibers these days. And because the overlap of the light with the glass is very low, very small, you can send pulses with extremely high intensity, which exceed 10 to the 14. Actually, we have indications that you can exceed 10 to the 15 watts per square centimeter in the core, which is an intensity way above the damage threshold or the ionization threshold of any material. Then the dispersion is very weak and just flat and just a bit anomalous, in the order of tens of femtoseconds square per centimeter, which means that if you send a few femtoseconds pulse in the fiber, this will propagate without disperse and without getting chirp upon propagation. You can see that the dispersion is flat, but we have some peaks, some regions where the dispersion explodes, and so the loss, the pink areas. But these regions, these are very well localized and depends on the thickness of the capillaries surrounding the fiber. So we can engineer the fiber to such that we can have these regions far away from where we want to work, and or even close to where we want to work. And this can change the propagation dynamics of our pulses inside the fiber. Okay, so then we can just take a fiber, we place it inside a gas cell, and then we close the gas cells, we evacuate, we fill the gas cell with gas, and then by just changing the gas pressure or the gas species, we can change the dispersion of the fiber and continuously shift the zero dispersion frequency all the way from the UV up to the near infrared. And at the same time, we can tune the nonlinear coefficients gamma. And this gives us a tremendous power over to control the nonlinear propagation of pulses. In fact, in nonlinear optics, there are these quantities which can determine the propagation dynamics of a pulse. And these are the dispersion lengths, which you see depends on the pulse duration divided by the dispersion. So we can tune this. The nonlinear length, which depends on the nonlinear coefficients gamma times the peak power, P. So we can tune this as well. And the Soliton order, which depends on the square roots over the ratio of the two. And then if we just fill the fiber with noble gas, we have only Kerr nonlinearities. And just by changing the Soliton order or the zero dispersion frequency, we can act on the propagation dynamics of the pulse and modify and access different regimes if we want. If we just select the dispersions such that the pressure such that the dispersion is normal, we can have temporal spectral broadening such that we can just broaden our spectrums and then recompress it using some optical elements. Or we can change the pressure such that we go in the anomalous dispersion and observe Soliton effects of compression or high-order Soliton. So here, what happens is that you generate new frequency components as your pulse propagates along the fiber, but then the negative dispersion brings the spectral components back, and this means that the pulse becomes much shorter. And if we increase the nonlinearities, we also increase, by increasing the pressure, we also increase perturbations, and when we compress these pulses, we can eventually observe Soliton fission and another phenomenon which is called dispersive wave emission, which we will see in a moment. If we then increase even further the gas pressure and the nonlinearities of the system, we will then observe modulation instability, a complete breakup of the pulses, which can then be used for generation of incoherent and flat, broadband and flat supercontinuum, which can be very useful, but I'm not going to tell you much about this today. And then if we replace the gas with a molecular gas, like hydrogen, we can also delay our pulses and, for example, redshift our pulses. But this is the story for another day. So this is one of the most beautiful and powerful aspects of nonlinear optics, in my opinion, which is scale invariant. This means that if you take a fiber, for example, the one on the left side, plot on the left side, you take a 60 micron core fiber, radius fiber, you can observe exactly the same propagation dynamics for different parameters in a smaller fiber, as long as you choose your scaling parameters in a suitable way. So you see here, the fibers are very different, the gas filling pressure are very different, but the propagation dynamics is absolutely identical, at least within 40 dB dynamic range. And the only thing which is different is the length over which this dynamics takes place, and you can see that in one case it's about 15 times longer, but this can be just recovered by looking at the compression length, which depends on the Soliton order, and the dispersion length, which we have learned that we can tune. So we got very interested in the scale invariance of the system, and we decided to explore this a bit more. And we then realized that scale invariance doesn't always hold. Actually, there are some limits. And especially if you are interested in Soliton effects of compression and you're interested in compressing your pulses, then these limits becomes especially important. So these limits are modulation and stability, which we have just seen, and then there are other limits set by high order dispersion and ionization. And within these limits, we can identify an optimal region where scale invariance holds and where optimal Soliton effects of compression is optimal. And then we can see that this region becomes much smaller for shorter pulses, and so the compression factors become smaller. So it means that if you start with a pulse which is 200 femtoseconds, you can compress it by a factor 20 easily, maybe even more. But if you start with a pulse which is 6 femtoseconds long, you can compress it by a factor 8, maybe 10 if you're lucky, which is still very good, but you need to know that. And even both numerics and preliminary results also from other groups show that you can indeed use this scheme to achieve attoseconds duration at the output of the fiber if you deliver your pulses directly to vacuum. So this would be very exciting to see when we can get there. And then you see that because of scale invariance, you can access many of these dynamics also in capillaries, but these capillaries don't have any structure, so are much more lossy. So you can expect that and in fact this is the case, that the region which scale invariance holds and which is optimal for Soliton effects of compression becomes much smaller, and also it is not fully invariant as it is in fibers, because the loss depends massively on the radius of the fiber. So the scale invariant doesn't hold the same way, it's radius dependent, but on the other hand, you can get much higher energies if you're interested, and this was the work of John Travers. So, and then once you understand this, you can get single cycle pulses, even shorter pulses, essentially at any wavelength, in the mid-infrared, from the mid-infrared all the way down to the UV at 400 nanometer, using pulse energy from tens of nanojoule up to hundreds of microjoule. And this are all our, so we show in collaboration with ICFO, single cycle pulses at 3 micron, then at 1030 we will see that in a moment at 400 nanometer, and again the group of John Travers managed to show even subcycles durations using this scheme with a capillary at 2 micron, and they achieved 2 femtoseconds pulses, which is considerably shorter than a single cycle. And a very important aspect, so people who knows a bit about solitons usually say solitons are noisy and you cannot preserve CP stability, but here actually we keep the soliton order quite low, so we can preserve the CP stability upon compression, as well as you can do with conventional self-phase modulation. Let me just continue a moment about the 3 micron pulses, because these are very powerful, give us a very powerful tool to generate even light at even shorter and longer wavelengths. And in fact, if you have such short pulses, which we generated by simply pumping single ring PCF with OPCPA delivering 100 femtoseconds pulses, then you can pump a lot of new magic crystals, as magic as this one, which is so magic that I cannot even pronounce the name. And then in doing intrapulse DFG, because you have such short pulses, you can generate a tremendously broad spectrum, spanning all the way from the ultraviolets up to 40 micron, which corresponds to terahertz. By changing the pressure, as you can see, you can enhance different part of the spectrum. So we can enhance the UV part or the terahertz part. And this is, again, CP stable radiation, which is at reasonably high repetition rates, and the 10 micron part corresponds to 86 femtoseconds measured via electro-optical sampling. And when we compare this with a synchrotron, so which is denoted by this dashed line diamond SLS, this is the brightest synchrotron we have in Europe, you can see that we can cover the entire spectral range covered by this synchrotron arm, and with a brightness which is several orders of magnitudes higher. So in a way we can say that we have taken a synchrotron and we squeezed this to the size of a fiber. Of course, the OPCPA is a bit larger than the fiber, but I think it's still considerably smaller than the synchrotron. Okay, so this was all very nice experiments, but at the beginning I mentioned that we want to go to very high repetition rates, and we don't care so much about the energy. So we started with fiber laser delivering 350 femtoseconds at 1 micron with average power up to 100 watts. And we sent these pulses to a fairly long fiber. This was almost 4 meters long, filled with 10 bar krypton. Here we used the fiber for cell-phase modulation. We broadened the spectrum, and then we used some chirp mirror to recompensate this. And you can see we obtained very nice pulses, 20 femtoseconds long, at 1, 5, and 10 megahertz repetition rates with a remarkable efficiency of 85%, considering all the optics. So actually, out of the fiber, we have 96%, but the optics are a bit lossy, with an average power exceeding 60 watts. Then we have such short pulses. We send this to another fiber. This time we did Soliton effect self-compression. In this way we could get very nice beam profile. This is the measured beam profile, it's not a simulation, with 3.8 femtoseconds, which are exactly a single cycle. Again, excellent transmission. And this, I believe, they are still the shortest pulses ever generated at 10 megahertz at such high repetition rates with a similar peak power. Okay, then we have seen that we can get very short pulses at high repetition rates, but what about generating radiation at different frequencies? And for this, we can exploit Soliton fission, resonant dispersive wave emission, and just increase slightly the pressure, or just increasing slightly the fiber length. And you see that after self-compression, the pulse breaks up. And if we look at the spectral domain, we see the appearance of well-defined sidebands at high frequency, in this case, at 1.2 micron. Why did this happen? Well, we know that solitons are stable because the propagation constant is very different from the propagation constant of a linear wave. But here we're talking about such broad spectra, so hundreds of terahertz, and we get eventually at high frequency a phase matching between the soliton propagation constant and the propagation constant of a linear wave, which means that by simply tuning the pressure or changing the energy, we can change the phase matching position and generate radiation at different frequencies, from the visible, and we see this here, all the way down to the vacuum and ultraviolet. So this, people often ask whether this is done all in the same fiber. No, these are different fibers, but for each fiber you can tune about 100, 150 nanometers, because then you need to play with the resonances. But still, it's remarkable broad tunability for many sources, and you can go to very short wavelengths to the vacuum UV. Here we were limited by the window at the output of the gas cell. And the efficiency is also excellent because you get 0.5% efficiency in the vacuum UV, and there are no many other sources which you can use with such efficiency. And again, carrier envelope phase is preserved, and you can have very broadband radiation which supports a few femtoseconds. So the problem with this is that in the UV everything is very dispersive. So if you want to measure it at the output of the gas cell, or even after propagating a few centimeters in a gas, this radiation will become easily tens or even hundreds of femtoseconds. So you cannot really measure. It's not to speak about the damage of the optics. So in collaboration with John Marangos at Imperial College, we just deliver the output of the fiber to vacuum using a pressure gradient. And then we use a frog to measure these pulses. And in this way, we could measure pulses as short as 3 femtoseconds, again, tunable at different wavelengths in the deep ultraviolet, 220 nanometer up to 300 nanometer. And this, again, were for a while the shortest pulses ever generated in the deep UV. Then in Hamburg, they managed to beat us by about 100 attoseconds, but I think it's okay. Okay, so this was everything at 1 kHz. Let's see what happens when we increase the repetition rate. For this, we use the short pulses which we generated out of our fiber laser, and we started working at 100 kHz and filling with the fiber either with neon, 53 bar, or helium, identical pressure. We could generate radiation at 260 nanometer or 205 nanometer with energies up to the microjoule level and up to 1 watt of average power. So this is a remarkable power in this spectral region. And in fact, we were very good at burning a lot of optics. As you can see the prism over there, you can see the beam paths of the UV glowing. But then we learned how to make, that we had to make huge beams, and then eventually we could measure these pulses. But then we tried to increase the repetition rates even further, and here weird things start happening. So the most simple thing is that if you increase the repetition rates, the power in UV doesn't scale linearly with the repetition rate, as we would expect, but it tends to saturate. But what is very weird is that if we look at the central wavelength of this dispersive wave, this shifts to longer wavelengths as we increase the repetition rates. So why is that? This has something to do with ionization of the gas, and even if helium has a higher ionization potential, actually we need to compress more to get there, so we are ionizing more helium than neon. So this comes, as I said, from ionization, because the pulses undergo self-compression, the peak intensity goes up and eventually ionize the gas filling the fiber. This corresponds to a change in the refractive index, which is very sharp and can give a change in the refractive index on the order of 10 to the minus 3. And it's directly proportional to the free electron density, which can be as high as 10 to the 18 or 19 electrons per cubic centimeter. And then the refractive index in principle stay constant over nanoseconds timescales. So argon has the longest recombination time, which is about a few tenths of nanoseconds. What is important to notice is that this is a very high order nonlinear process. So the transversal refractive index, it's not longer homogeneous across the fiber. And so you will have higher electron density at the very center of the fiber, and then you will have fewer electrons as you go closer to the board and to the end of the fiber. And this gives a distortion of the special modes, and because free electrons have a strong dependence on the wavelength, it also depends very much on the wavelengths at which he operates. This means that if you have a delayed process, this like dispersive wave, which is generated delayed, this will observe completely different fiber environment, and this in parts explain why we got this dynamics of worse efficiency and redshifting pulses. But this is on tens of nanoseconds time scale, but the time between the pulses is still on the microseconds time scale. And so it doesn't fully explain what's going on. So if we want to, turns out that everything is much more complicated. So to understand this, we can look at this short video. What happens is that after recombination, you have a pressure wave propagating outwards from the center of the fiber. And this pressure wave eventually hits the capillary, which start vibrating and reflect the pressure wave all the way. And this creates a very complex refractive index profile across the fiber. These are simulations, but actually we know that all this is true because we were able to measure this, including the deflection of the capillaries, which was on the order of few nanometers. I don't have time to tell you how we measure it, but here we can see the change of refractive index as function of time measured here, and we see that there is a very deep change, fast change of the refractive index, and then it recovers over tens, even hundreds of microseconds time scale. And if we if we then use different spatial modes with these techniques, you see that different spatial modes have different spatial profile. So we can sense, we can see how the refractive index changes is different at different positions, because they will sense a different refractive index, and so we can get informations about what's going on inside the fiber. And this becomes much clearer if we look at a zoom on a shorter time scale. You can see this initial peak over the first nanoseconds. These are the free electrons, and after the recombination, you can see many different curves with many different peaks. As low modulations, these low modulations are the pressure waves being bounced back and forth, while this fast modulation here are the capillary vibrating. And you see that you have different maxima because these are given by the speed of sound in the gas and by the different mechanical modes which we can so observe. And this was all measured via techniques which we developed at MPL, which is prism-assisted side coupling. Okay, but, what is important is that when we work at megahertz or 10 of megahertz repetition rates, we are essentially interested on the, what happens is that we will have a build-up process, the phase will build up, but we are still looking at the very tail of this. So what happens is that the temperature will change and becomes higher and higher, but we can, because of the time scales involved, we can neglect all the pressure waves and the acoustic waves, the dynamics. So we can simply describe the system using a simple diffusion equation, and then we can recognize that there are two major contributions. One is given by thermal diffusivity, and we see that this depends on the thermal conductivity and inversely on the gas density. And then a source term, which depends on the free electron density and the ionization potential. And then if we run some simulations, you can see that the index saturates within a few tens of pulses, and this phase change increases dramatically with repetition rate as expected, peak intensity, but also with gas pressure. So if we want to minimize this, we need, on the one hand, to minimize ionization. We can do this by lowering the Soliton order or the ionization potential to suppress the source term, but this means also lower nonlinearity, or lowering the pressure, but this also means lower nonlinearity. So this is good in a way for Soliton effects of compression, but not always, but it's not ideal anyway. So then we decide to explore other routes, and this is just gas mixtures. It's very simple. If you mix krypton with helium, you can take advantage of the thermal conductivity of helium and take advantage of the nonlinearity of krypton without making any change. And then just simple calculations show that we can get a thermal diffusivity which is 4 times larger while keeping the same nonlinear refractive index. So we did experiments. We filled, in this case, a capillary with krypton, and using a side interferometer, we measured the relative phase change between a probe and a reference pulse. And we measure in this way 200 millirads change in the phase, but also a very noisy phase, which this is due mostly to the acoustic waves going back and forth. Then we increase the pressure of helium, and you see that as we increase the pressure, we could suppress both the phase change, and also we could make this line much thinner than it was for the case of no krypton. And actually, it turned out that, as I often said, it's one of the few experiments which are better than theory. So when we compared this with theory, we could get a very good agreement for the case of no helium and 1 bar of helium. But simulations predict that if we have 5 bar helium, we don't suppress as much as we see in the experiments. So this doesn't, and then we see that this gives a suppression of this phase change, which is larger than 43 times. So it's a very good way to cool our system. So just moving toward the conclusions, I would like to stress that these effects of long-lived dynamics in gases have been studied and observed for a long time in the field of filamentation at low repetition rates, hundreds of hertz of kilohertz. And here have been exploited for making waveguides, for example, for high-power lasers or for plasma waveguides, but also for fog clearance. More recently, as I mentioned, we have observed such effects at high repetition rates in fibers, but this is also known in femtoseconds enhanced cavities. So understanding these effects is not only important to understand how to increase the repetition rates, but actually I hope that we can get some new cool insights or maybe some new cool applications like they did in free space. And with this, I would move to the conclusions. So I've told you how we can generate very short pulses at high repetition rates with tens of watts average power, or also at different frequencies, all the way from the vacuum UV up to the terahertz. I've briefly discussed scale invariance, and then, what happens when you pump too hard and you ionize at high repetition rates. And with this, I would like to conclude with the acknowledgements. I would like to thank Philip and Michael, the people I work with, and all my previous group members, Felix, Daniel, Johannes, Malika, and Alexei, and of course all my collaborators. Thanks.
Questions, please. There's one back there in the back, and I think you need this.
Thank you so much. That was a great talk. I just have a couple questions.
Yep.
The first one is, why is the theory worse? What are you assuming, and the experiment is not assuming? And the second question is, have you thought about maybe a coherent type of interplay between the light and the phonons, basically, that are happening, and can that be used for information processing? Thank you.
Yes. So theory doesn't work because we don't consider all the pressure waves, because for that we need to solve a much more complicated system, and a diffusion equation is much simpler to solve. But it seems that pressure waves dissipates much more energy than we expected, so this is very cool. So coherent, I'm not sure whether this is coherent. So we explored this in the case of hydrogen, for example, where there is some coherence. So we explored this numerically. You can extract energy from the system sending a delayed pulse. And this it's potentially very interesting. But on the other hand, hydrogen absorbs more than a noble gas, so it's not a large gain. And the rest of the dynamics I don't think are coherent. At least I don't understand them as a coherence process, so I don't think we can extract energy.
Thank you very much for your interesting talks. I have a question regarding the noise. Did you measure the noise, the first? And second, how did you reduce the number of the Soliton fission? By reducing the power or by changing the, let's say, gas pressure?
Exactly. So we change, the noise, we measured the RIN of the single cycle pulses at 10 megahertz. And if I remember, this was, the integrated RIN was about 0.4%, something like this, but was just slightly higher than the laser. So it was really comparable to the noise of the laser. You change the Soliton order, and so the noise just by changing the power, the pulse duration, or the gas pressure. So these are the parameters.
So Francesco, what about the micro rocket?
Thanks. I was hoping someone asked about that. So micro rockets are super cool. What happens is you do trapping. So you can trap a particle inside the fiber just using CW pulses. And then if you send a short pulse into the fiber, just with hundreds of nanojoule energy, the femtoseconds pulse will be focused by the silica particle and will be focused on the rare surface of the particle. And this will create a plasma jet, and you pull the fiber, and you can accelerate till the speed of sound, which is over 2 orders of magnitude faster than any other particle acceleration experiments. So initially, we did this because we wanted to coat the inner core of the fiber. Not sure this is exactly the right way to do it, but it's very cool, and maybe for nanomedicine where you need to deliver drugs in precise locations can be quite interesting.
So first of all, it was a great talk. Thank you so much. Question, did you see behavior of rogue waves, which was a very exciting topic at one point?
Rogue waves. I did look at this during my PhD studies. So for rogue waves, you need to be essentially in the modulation and stability regime. And what happens here, it's quite interesting. I got very excited, but then I was told that it's not interesting, so I had to stop. So when you have modulation and stability, what happens is that you launch a pulse, and this breaks into a train of pulses, which are much shorter. And then if you look at the statistics of the peak intensity of peak power of these pulses, and you have rogue waves, you will observe this L-shape, well, these different statistics. So back at the time, I did some numerical studies of this, and especially I considered the case, what happens when you increase the nonlinearity so much that you break your initial pulse in pulses which are shorter than the duration of a single cycle. And what happens is that the statistics does change. It's you observe a completely different statistics, which more extreme events, but it was very different from the common statistics of rogue waves. After that, I was told that it was not interesting, so I had to stop.
If you'll permit the guy running around with the microphone to ask a question. I have a naive question about the frequency conversion. Clearly, you're able to dictate what nonlinearities and the modes and the dispersion amongst them. So to me, that says that you can have, say, very high efficiencies of THG. And if you can do that, couldn't you then also do spontaneous parametric down conversion in a similar way, and maybe even get at intensities where there's squeezed light? Is that something that's been explored? Can you comment on that?
Yeah, I mean, you can do it. In that work, we were mostly interested in intrapulse DFG, because in this way you can ensure carrier envelope phase stabilities. And but yeah, sure, you can look at this, but for that you don't need, I would say, such short pulses. Yeah.
Okay, I think we've run out of questions, so I want to ask one question before we end, and then I'll ask Bob to come up and we'll say a few words. So through all of your talk, you've changed the frequency of the radiation a lot. You've changed different sizes of fibers and things like that, yet you speak very rarely, if at all, about modes of the fiber. Presumably there are multiple modes there.
Mm-hmm.
Do you stay within a mode? Do you couple between modes and filter down to the most fundamental, or what? Can you speak?
Sure, this is a good question. So we mostly work in the fundamental mode. Some fibers, these fibers can be made single mode if we want. So they are not single modes like solid core fibers. They are single mode in the sense that the loss of I-order modes is about 10, 100 times higher. So this can help if we have problems. But then, of course, we have such nonlinear, extreme nonlinear dynamics, which we can have conversion to I-order modes. This happens especially in the case of Raman. So if we launch short pulses in gas hydrogen filled fiber, we can observe the mode conversion at different wavelengths. And also for dispersive waves. But typically, so for kernel linearities, what happens is mostly very weak change in the order of few percent in the worst case. In the case of Raman, you can have massive conversion, but are at wavelengths which are different because you have phase matching process. So the dispersion for each mode is different. So if we are interested in some dynamics, for example, if we want to redshift the pulse, the redshifted pulse in a hydrogen filled fiber will be all in the fundamental modes, but we can get some I-order modes at higher frequencies. And in the case of ionization, actually, if you ionize too much, you observe donut modes, but it's not because we get coupling between different modes, but this is because the fundamental mode of the waveguide becomes a donut mode. That's it.
So thank you very much. And Bob, can I invite you to come up? Oh, thank you.